All right, so now we're going to cover what's called the remainder theorem. If the polynomial p of x is divided by x minus c, then the remainder is the value of p evaluated at c. So what does this mean? Basically, if you divide a polynomial by x minus 3, then the remainder that you get from that division is going to be the function evaluated at 3. That shouldn't seem too trivial, although we did kind of hint to it a little bit up here whenever I said if it's a 0, then whenever you divide by x minus 2, the remainder is 0. So the fact that the function value is 0 and the remainder is 0 kind of hints to the fact that the remainder is the function value, but that's a little bit strange. Let's just do this. First of all, if I wanted to evaluate p of negative 7, it would be very hard to plug in a negative 7 because I'd have to take negative 7 to the 4th power and then multiply it by 5, and then, it's a lot of work to plug it in. But synthetic division is easy. So what I'm going to do here is I'm going to use the remainder theorem to evaluate this function at this value. And then I'm going to try to explain to you why the remainder theorem works. So I'm going to divide by the factor x minus a negative 7. X plus 7. So this is the factor I'm dividing by to evaluate it at negative 7. But the c value is negative 7. So this is the number I put into my synthetic division. So 5, 34, again, no x squared term. For some reason, I don't like x squared terms. 52, negative 50. You have to put this placeholder in here. That's the common mistake the kids make on tests. So I'm going to evaluate this at negative 7. I'm going to divide out an x plus 7, but my c value is negative 7. Do the synthetic division. Drop down the 5, multiply, add, multiply, add, multiply, add, multiply, add. So this is my remainder. And according to this theorem, my remainder is my function evaluated at negative 7. So I just plugged in negative 7 into this and calculated and got negative 64. Now, in class, we actually plugged it into our calculator to verify that if you plug this in for x, you actually do get a negative 64, and it works. You can verify it if you'd like to. Pause the video if you want. So the next thing then is why does this thing work? Why, when I synthetically divide this out, why does my remainder come out to be my function value? So I'm going to illustrate this by writing this division using the division algorithm. Division algorithm, you take your dividend, it's equal to your divisor. My divisor would be x plus 7. My quotient, which is 5x to the x squared, x to the third constant, so x to the third minus x squared plus 7x plus 2 plus my remainder, or minus 64. So here's the question. I can plug in x equals negative 7 into this, but this is the same as this side here. So I could also plug in x equals negative 7 into this. So my question for you would be then, do you guys see why it's difficult to plug in x equals negative 7 into this? And do you see why it's going to be really, really easy to plug it into this? Now, I don't want to plug negative 7 into this, but if I plug negative 7 into this one, I'm going to get a 0. And 0 times any crazy number that this is going to wipe that out and make that 0. And 0 minus 64 has got to be a 64. So the idea here is it's really easy to plug in x equals negative 7 into this because this is one of the factors. It's going to zero it out. Therefore, my remainder is going to be my function value at that spot. Hopefully that makes sense. If not, you can just remember the remainder is the function value at that spot. Okay? So this is an easy way to evaluate polynomials at ugly numbers. Easier way. Okay? Show that the polynomial below has zeros of 3 and negative 2. then use this information to find all the zeros of the polynomial, okay? Well, if this is a zero of the polynomial, then an x-intercept must be 3. And if an x-intercept is 3, then x minus 3 must be a factor. And if x minus 3 is a factor, then when I do the division, my remainder should be 0. So this is how I'm going to verify that 3 is a 0. I'm just going to synthetically divide it and see if my remainder is 0. So here we go. 1, negative 3. Ooh, we've got a quadratic. We've got an x squared term. Let's take out a positive 3. We take out the 0. We take out the x-intercept. It's an x minus 3 factor. Drop down the first number. Multiply, add, multiply, add, multiply. Oops. Multiply, add, multiply, add. So it's not a coincidence that this is a 0. If that's a 0, then that means x equals 3 is a 0. That means this is an x-intercept. That means this is a factor. So I just proved that this was a 0. And if I write this with the division algorithm, I started with this. And now I could write this as x minus 3 times x squared, x to the third, minus, oh, we're back omitting the x squareds, all right. So I just factored this from a 4th degree into a linear times a 3rd degree. By the way, every time you take out a linear term, it's going to lower the degree by 1. So now, let's show that this is a 0 of the polynomial, that x plus 2 is a factor. But don't start back at square 1. I've already reduced it down from a 4th degree to a 3rd degree. Let's just take the negative 2 out of this one. After all, if this is a 0 of this, then it must also be a 0 of that, right? So don't go back to the start. Keep reducing it down. So now I'm going to take out a negative 2, an x plus 2 factor. Drop it down, multiply, add, multiply, add, multiply. Of course, I get another 0. So I just showed that negative 2 is a 0, that this is a factor. And now I'm down to x squared. So now I've reduced it down, I've factored it into x minus 3. Then this breaks down into an x plus 2 and an x squared minus 2x minus 1. So now, to find the last zeros, I could just try to solve this or try to factor that. Fortunately, it's not factorable. Factors of negative 1 that add up to negative 2, yeah, that's not going to work. So it's not factorable, but I have other techniques for finding the 0. I'm going to just take that x squared minus 2x minus 1, set it equal to 0, and ask, what values of x make the function 0? That's the definition of a 0. I could use a quadratic formula or complete the square. I'm a mathematician, so of course I'm going to complete the square. Quadratic formulas for noobs. Half of this, negative 1 squared, positive 1, add 1 to both sides. X minus 1 squared equals 2. Square root both sides. Don't forget the plus or minus. X minus 1 is equal to plus or minus the square root of 2, so x is equal to 1 plus or minus the square root of 2. So, the zeros are x equals 3, negative 2, 1 plus the square root of 2, and 1 minus the square root of 2. Those last two zeros, this has got 4 x-intercepts, 4 zeros. The last two zeros happen to be irrational numbers. Still x-intercepts. These are actual numbers. I mean, they're real, right? So they are actual x-intercepts. It's just hard to approximate them. And where we're going with this eventually is, if these are zeros, then x minus 1 plus root 2 has to be a factor, right? Just like x minus 3 is a factor if 3 is a 0. Well, this is a factor if this is a 0 also. That's kind of where we're going here next lesson, okay? Last one. Oh, 10 minutes.